Ground fault circuit interrupters, or GFCIs, function to protect against electrical shock by detecting an imbalance in current flow between the hot and neutral wires. The mechanism behind this protection is that when an imbalance occurs, such as current leaking to ground due to a fault, the GFCI trips and breaks the circuit. GFCIs are required for outdoor receptacles, bathrooms, kitchens, and other wet or damp locations where electrical shock hazards are present. Arc fault circuit interrupters, or AFCIs, function to protect against electrical fires by detecting dangerous arcs, which are electrical discharges that can ignite fires. AFCIs monitor the electrical current waveform and detect patterns that indicate the presence of an arc. Arcs can be caused by loose connections, damaged wires, or equipment malfunctions. AFCIs are required for bedrooms in most jurisdictions due to the increased fire risk associated with electrical devices such as lamps and electronics used in these areas. A GFCI tester simulates a ground fault by creating an imbalance in current flow. However, AFCIs do not respond to this type of fault. AFCIs are designed to detect arcs, which are not created by the GFCI tester. AFCIs are generally more expensive than GFCIs. AFCIs can sometimes experience false trips, especially if they are not properly installed or if there are loose connections. It is important to always follow local electrical codes and the inspector's instructions when installing AFCIs and GFCIs. Both AFCIs and GFCIs provide additional protection against electrical hazards, and their use is highly recommended in both residential and commercial settings. To elaborate further, let's consider the specific differences in how these devices operate and the hazards they are designed to address. A GFCI is primarily concerned with preventing electrical shock to people. It constantly monitors the current flowing in the hot and neutral conductors of a circuit. Under normal conditions, the current flowing through both conductors should be equal. However, if a fault occurs, such as someone touching a live wire, a portion of the current may flow through their body to ground instead of returning through the neutral wire. This creates an imbalance in the current flow, and the GFCI detects this imbalance. Even a small difference, as little as 5 mA, is enough to trigger the GFCI to trip, quickly cutting off the power to the circuit and preventing a potentially fatal electric shock. The speed at which a GFCI trips is also crucial, typically within a fraction of a second. This rapid response time minimizes the duration of the shock, significantly reducing the risk of serious injury or death. GFCI protection is essential in areas where water is likely to be present because water greatly increases the risk of electrical shock. This is why they are mandated in locations like bathrooms, kitchens, outdoor receptacles, and near swimming pools. AFCIs, on the other hand, are designed to prevent electrical fires. They detect arcs, which are unintended electrical discharges that can generate intense heat. Arcs can occur for various reasons, including damaged or frayed wiring, loose connections, and faulty appliances. These arcs can produce temperatures high enough to ignite nearby flammable materials, such as wood, paper, or fabric, leading to a fire. Unlike GFCIs, AFCIs do not simply monitor the current balance. Instead, they analyze the shape of the current waveform for patterns that are characteristic of arcing. This requires more sophisticated electronics and signal processing capabilities. AFCIs can detect different types of arcs, including series arcs, which occur when a wire is broken or partially severed, and parallel arcs, which occur between two conductors. AFCIs are particularly important in bedrooms because these areas often contain a high concentration of electrical devices and flammable materials. Lamps, phone chargers, and other electronic devices can all be potential sources of arcs. Requiring AFCI protection in bedrooms significantly reduces the risk of electrical fires, protecting occupants while they sleep. The reason why a GFCI tester will not trip an AFCI is due to the fundamental difference in their detection methods. A GFCI tester works by creating a simulated ground fault. It introduces a small current leakage to ground, creating an imbalance that a GFCI would normally detect. However, an AFCI is not designed to respond to this type of imbalance. Instead, it is looking for the specific waveform patterns associated with arcing. Since the GFCI tester does not generate an arc, the AFCI will not trip. Think of it like this: a GFCI is designed to detect a leak in the plumbing system, while an AFCI is designed to detect a spark near flammable materials. A tool designed to find leaks will not be useful for finding sparks, and vice versa. It's also important to note that AFCIs and GFCIs are not mutually exclusive. In many cases, both types of protection are required in the same location. For example, an outdoor receptacle may require both GFCI protection to prevent electrical shock and AFCI protection if it is part of a circuit serving a bedroom. When installing AFCIs, it's crucial to follow the manufacturer's instructions carefully. Improper installation can lead to nuisance tripping, where the AFCI trips even when there is no actual arc fault. This can be caused by electrical noise or other interference on the circuit. Loose connections can also cause AFCIs to trip, as they can create small arcs. Therefore, it's important to ensure that all connections are tight and secure. Despite the potential for nuisance tripping, the benefits of AFCI protection far outweigh the drawbacks. By detecting and interrupting arc faults, AFCIs can prevent electrical fires and save lives. In summary, GFCIs protect against electrical shock by detecting current imbalances, while AFCIs protect against electrical fires by detecting arc faults. A GFCI tester will not trip an AFCI because it does not simulate an arc. Both types of protection are important for electrical safety, and their use is highly recommended in residential and commercial settings. Understanding the specific function of each device can help in ensuring electrical systems are safe and compliant with electrical codes. Electrical codes are the set of rules and regulations governing the safe installation and maintenance of electrical systems. These codes are designed to protect people and property from electrical hazards such as shock and fire. Electrical codes vary from place to place, but they are typically based on national standards such as the National Electrical Code, or NEC, in the United States. The NEC is a comprehensive set of guidelines that covers virtually every aspect of electrical installation, from wiring methods to grounding and bonding. Local jurisdictions may adopt the NEC in its entirety or may modify it to suit their specific needs. Electrical inspectors are responsible for enforcing electrical codes. They review electrical plans, inspect electrical installations, and issue permits to ensure that all work is done in accordance with the code. The electrical inspectors play a crucial role in ensuring electrical safety. They have the authority to reject any work that does not meet code requirements, and they can require corrections to be made before the installation is approved. When wiring a house, it's essential to follow the electrical code carefully. This includes using the correct types of wiring, properly grounding and bonding the electrical system, and installing AFCIs and GFCIs where required. It's also important to obtain the necessary permits and inspections to ensure that the work is done safely and legally. Failure to comply with electrical codes can result in fines, delays, and even legal action. More importantly, it can put people and property at risk. If someone is not familiar with electrical codes, it's best to hire a qualified electrician to do the work. A qualified electrician has the knowledge and experience to ensure that the electrical system is installed safely and in accordance with the code. Grounding and bonding are two important concepts in electrical safety. Grounding is the process of connecting the electrical system to the earth. This provides a low resistance path for fault current to flow back to the source, which helps to trip the circuit breaker or fuse and clear the fault. Bonding is the process of connecting all of the metal parts of the electrical system together. This ensures that all of the metal parts are at the same electrical potential, which reduces the risk of electric shock. Both grounding and bonding are essential for electrical safety. They help to protect people from electric shock and prevent electrical fires. There are several different types of grounding systems, including the grounded system, the ungrounded system, and the impedance grounded system. The grounded system is the most common type of grounding system in residential and commercial buildings. In a grounded system, one of the conductors is intentionally connected to ground. This conductor is typically the neutral conductor. The ungrounded system does not have any intentional connection to ground. This type of system is typically used in industrial applications where a high degree of reliability is required. The impedance-grounded system uses an impedance to limit the amount of fault current that can flow to ground. This type of system is typically used in applications where a high degree of safety is required. Bonding is typically accomplished by connecting all of the metal parts of the electrical system together with bonding jumpers. Bonding jumpers are typically made of copper wire or busbar. The size of the bonding jumpers must be sufficient to carry the maximum fault current that could flow through the system. In addition to grounding and bonding, surge protection is another important aspect of electrical safety. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, utility switching, or other electrical disturbances. SPD work by diverting the surge current to ground, preventing it from damaging sensitive electronic equipment. SPD are available in a variety of types and sizes. They can be installed at the service entrance, at branch panels, or at individual pieces of equipment. It's important to choose the right type and size of SPD for the application. When installing SPD, it's important to follow the manufacturer's instructions carefully. Improper installation can render the SPD ineffective. Electrical safety is a complex topic, but it's essential to understand the basics. By following electrical codes, properly grounding and bonding the electrical system, and installing surge protection devices, one can significantly reduce the risk of electrical hazards. Let's delve deeper into the specific requirements for AFCIs and GFCIs in different areas of a home or building, referencing the National Electrical Code, or NEC, where applicable. The NEC is updated every 3 years, so it's crucial to consult the latest edition for the most current requirements. For GFCIs, the NEC specifies where GFCI protection is required to protect people from electric shock. Section 210.8 of the NEC covers GFCI protection for personnel. This section requires GFCI protection for 125-volt, 15 and 20 ampere receptacles installed in various locations, including bathrooms, garages, outdoors, crawl spaces, unfinished basements, kitchens, and laundry areas. In bathrooms, GFCI protection is required for all receptacles, regardless of their proximity to sinks or other water sources. This is because bathrooms are inherently wet environments and the risk of electric shock is higher. In garages, GFCI protection is required for all 125-volt, 15 and 20 ampere receptacles that are not readily accessible. This includes receptacles that are behind appliances or located in hard-to-reach areas. Outdoors, GFCI protection is required for all 125-volt, 15 and 20 ampere receptacles that are accessible to the public. This includes receptacles on decks, patios, and balconies. Crawl spaces and unfinished basements also require GFCI protection for all 125-volt, 15 and 20 ampere receptacles. These areas are often damp and can be hazardous. In kitchens, GFCI protection is required for all 125-volt, 15 and 20 ampere receptacles that serve countertop surfaces. This is because kitchens are another area where water is commonly present. Laundry areas also require GFCI protection for all 125-volt, 15 and 20 ampere receptacles. In addition to these specific locations, the NEC also requires GFCI protection for certain types of equipment, such as swimming pool equipment, hot tubs, and spas. For AFCIs, the NEC specifies where site protection is required to protect against electrical fires. Section 210.12 of the NEC covers arc fault circuit interrupter protection. This section requires AFCI protection for all branch circuits that supply 120-volt single-phase, 15 and 20 ampere outlets installed in dwelling units. This includes outlets in bedrooms, living rooms, dining rooms, family rooms, recreation rooms, and other similar areas. The purpose of this requirement is to reduce the risk of electrical fires in homes. As mentioned earlier, bedrooms are a particularly high-risk area due to the presence of flammable materials and electrical devices. The NEC allows for certain exceptions to the AFCI requirements. For example, AFCI protection is not required for branch circuits that supply only fire alarm systems or smoke detectors. This is because these systems are critical for life safety, and nuisance stripping of the AFCI could disable them. The NEC also allows for the use of a combination AFCI/GFCI device in certain situations. A combination AFCI/GFCI device provides both arc fault and ground fault protection in a single unit. This can be a convenient option in areas where both types of protection are required. It's important to note that the NEC is a minimum standard. Local jurisdictions may have additional requirements for AFCIs and GFCIs. Always check with the local building department to determine the specific requirements in the area. When installing AFCIs and GFCIs, it's important to follow the manufacturer's instructions carefully. Improper installation can lead to nuisance tripping or even failure of the device. It's also important to test AFCIs and GFCIs regularly to ensure that they are functioning properly. Most AFCIs and GFCIs have a test button that can be used to verify their operation. By understanding the specific requirements for AFCIs and GFCIs, one can help ensure that their electrical system is safe and compliant with electrical codes. Let's consider some real-world scenarios to illustrate the importance of AFCIs and GFCIs. Imagine a scenario where someone is using a hairdryer in the bathroom. The hairdryer has a frayed cord and the wires are exposed. If the person touches the exposed wires, they could receive a severe electric shock. However, if the bathroom receptacle is protected by a GFCI, the GFCI will quickly trip, cutting off the power to the receptacle and preventing the electric shock. Now imagine a scenario where someone has a lamp in their bedroom. The lamp has a loose connection and an arc is forming inside the lamp. The arc is generating heat, and the heat is starting to ignite the nearby curtains. However, if the bedroom circuit is protected by an AFCI, the AFCI will detect the arc and trip, cutting off the power to the circuit and preventing the fire. These are just two examples of how AFCIs and GFCIs can save lives and prevent property damage. They are essential safety devices that should be installed in all homes and buildings. When choosing AFCIs and GFCIs, it's important to select products that are listed by a recognized testing laboratory, such as Underwriters Laboratories or all. UL-listed products have been tested and certified to meet safety standards. It's also important to choose AFCIs and GFCIs that are compatible with the electrical system. AFCIs and GFCIs are available in different voltage and amperage ratings. Choose the correct rating for the circuit that is being protected. Let's discuss some common misconceptions about AFCIs and GFCIs. One common misconception is that AFCIs and GFCIs are interchangeable. As we have discussed, this is not the case. AFCIs protect against electrical fires, while GFCIs protect against electrical shock. They serve different purposes and should not be used interchangeably. Another common misconception is that AFCIs and GFCIs are only required in new construction. While it's true that the NEC requires AFCIs and GFCIs in new construction, it's also a good idea to install them in existing homes and buildings. AFCIs and GFCIs can provide valuable protection against electrical hazards, regardless of the age of the building. Another common misconception is that AFCIs and GFCIs are foolproof. While AFCIs and GFCIs are very effective at preventing electrical hazards, they are not foolproof. They can fail to operate properly if they are not installed correctly or if they are damaged. That's why it's important to test AFCIs and GFCIs regularly to ensure that they are functioning properly. Another common misconception is that AFCIs and GFCIs are a substitute for proper wiring practices. AFCIs and GFCIs are designed to protect against electrical hazards that can occur even when the wiring is done correctly. However, they are not a substitute for proper wiring practices. It's important to follow electrical codes and use proper wiring methods to minimize the risk of electrical hazards. In conclusion, AFCIs and GFCIs are essential safety devices that should be installed in all homes and buildings. They protect against different types of electrical hazards, and they are not interchangeable. It's important to choose products that are listed by a recognized testing laboratory and to follow the manufacturer's instructions carefully. It's also important to test AFCIs and GFCIs regularly to ensure that they are functioning properly. By understanding the specific function of each device and following proper wiring practices, we can help ensure that our electrical systems are safe and compliant with electrical codes.